Close your eyes and feel yourself falling. Not the sudden drop that makes your stomach lurch, but a slow, infinite descent into something vast and patient. This is not a fall into danger. This is a fall into the deepest quiet the universe can offer. This is the fall across the event horizon. You have felt gravity your entire life. It has pressed against the soles of your feet, pulled blood downward through your veins, shaped the curve of your spine. Gravity is so familiar that you forget it is there, this invisible architecture that holds you to the world. But now, imagine a place where gravity becomes something else entirely. Not the gentle tug of Earth, but a pull so profound that even light cannot resist it. A place where the fabric of space and time bends so deeply that the universe itself seems to fold inward, creating a boundary beyond which nothing, not matter, not energy, not information, can ever return. This place exists. It is called a black hole, and at its edge lies the event horizon, the point of no return, the threshold between the universe you know and a realm of absolute darkness. Tonight, as your breathing slows and your thoughts begin to drift, we are going to cross that boundary together. We are going to fall past the edge of everything and explore what lies inside the most extreme environment the cosmos can create. There is something almost comforting about contemplation of the event horizon. It represents the ultimate surrender, the final release from all resistance. Beyond this invisible border, there are no more choices to make, no more paths to choose. There is only one direction inward, toward the singularity at the center. In this certainty, in this absolute inevitability, there is a kind of peace. The event horizon does not ask anything of you. It does not judge or resist. It simply is, patient and eternal, waiting at the edge of space-time itself. As you settle into comfort, let your mind prepare for this journey. We will move slowly, as all things must when approaching such extreme gravity. We will take time to understand what a black hole truly is, how it forms, and what it means to cross the boundary that separates inside from outside. We will explore the strange physics that governs this realm, where time and space exchange roles, where the future becomes a place rather than a moment, and where the ordinary rules of causality bend into new and unexpected shapes. You are safe here in this exploration. This is a journey of imagination and understanding, a way to touch the most extreme edges of physics without risk, without fear. And as we drift together toward that absolute darkness, you may find that the experience becomes a meditation, a gentle descent into concepts so vast and so strange that the everyday concerns of life begin to seem very small and very distant, like stars fading into the background as we fall deeper into the gravitational well. So breathe slowly. Let your body relax into the surface beneath you. Feel the familiar pull of Earth's gravity, knowing that we are about to explore a place where that gentle force becomes something unimaginably stronger, a pull that shapes not just matter, but the very structure of reality itself. We are going to fall together, you and I, past the point where light bends back on itself, past the boundary where time stretches toward infinity, and into the heart of darkness where the universe keeps its deepest secrets. This is the journey inside the event horizon. Let us begin. Before we approach the edge, we must understand what we are approaching. A black hole is not a hole at all, not in any ordinary sense. It is not an empty space or a tunnel through the cosmos. It is an object, a region of space-time where gravity has become so intense that it has curved the fabric of reality into a trap from which nothing can escape. To understand this, we must think differently about gravity itself. Imagine space-time as a fabric, a smooth and flexible surface that stretches across the entire universe. Mass and energy create curves in this fabric. A planet makes a gentle dip, like a marble resting on a stretched sheet. A star creates a deeper well. The more mass you concentrate in a smaller space, the steeper the curve becomes. Now imagine taking a star's worth of mass, perhaps 3 times the mass of our Sun, and compressing it down not to the size of a planet, not to the size of Earth, not even to the size of a mountain, but continuing to compress it until all that mass occupies a region smaller than a city, smaller than a building, smaller than a room. The curve in space-time becomes so steep, so extreme, that it closes in on itself. The dip becomes a bottomless well. This is a black hole. The edge of this well, the point where the curve becomes so steep that not even light can climb back out, is the event horizon. It is not a physical surface. You could not touch it or bounce off it. It is simply the mathematical boundary that separates 2 regions of space-time, inside and outside, escape and capture, the universe of light and the realm of absolute darkness. The event horizon is determined by a precise radius from the center of the black hole, a distance calculated by one of the most elegant equations in physics, derived by Carl Schwarzschild in 1916, just months after Einstein published his general theory of relativity. The Schwarzschild radius, as it is called, depends only on the mass of the black hole. For an object with the mass of our Sun, this radius would be about 3 kilometers. Compress the Sun down to a sphere 6 kilometers across, and it would become a black hole. Its event horizon would sit at that 3-kilometer mark, forming an invisible spherical boundary in space. For a black hole with 10 times the Sun's mass, the Schwarzschild radius would be 30 kilometers. For a supermassive black hole at the center of a galaxy, with 1 billion times the Sun's mass, the event horizon might stretch for billions of kilometers, larger than the orbits of the inner planets in our solar system. But regardless of size, the event horizon always marks the same fundamental transition. Outside this boundary, if you have a powerful enough rocket, you could still escape. You could fire your engines and climb back up the gravitational well, fighting against the pull until you reach safety. Inside this boundary, no amount of thrust, no matter how powerful, can bring you back out. The escape velocity exceeds the speed of light, and since nothing can travel faster than light, nothing can escape. The event horizon is not a barrier that pushes you back. It is a region of space-time where all forward light cones, all possible futures, point only inward. Let us imagine the formation of such an object, for understanding its birth helps us grasp its nature. Black holes form in several ways, but the most common begins with the death of a massive star. Throughout its life, a star is engaged in a constant battle between 2 forces. Gravity pulls inward, trying to compress the star into the smallest possible space. Nuclear fusion in the core generates outward pressure, heat, and radiation that push back against gravity's crush. For millions or billions of years, these forces balance, and the star shines steadily. But fusion cannot continue forever. Stars burn through their nuclear fuel in stages, fusing hydrogen into helium, then helium into carbon and oxygen, then progressing through heavier and heavier elements. For the most massive stars, this process continues until the core is made largely of iron. Iron is special. It is the most stable element in the universe. Fusing iron into heavier elements does not release energy. It consumes energy. When the core becomes iron, fusion stops. The outward pressure vanishes. In an instant, on a timescale of less than a second, gravity wins. The core collapses. Material that was once spread across thousands of kilometers compresses into a sphere perhaps 20 kilometers across. The density becomes unimaginable, comparable to cramming the mass of the Sun into a sphere the size of a city. Electrons are crushed into protons, forming neutrons. The collapsing core becomes a neutron star, held up by the quantum pressure of those neutrons refusing to occupy the same space. But if the core is massive enough, even this quantum pressure is not enough. If the collapsing core has more than about 2 to 3 times the sun's mass, nothing in the known laws of physics can stop the collapse. The neutrons themselves are crushed. The core continues to shrink, growing denser and denser, the gravitational pull at its surface becoming stronger and stronger until the escape velocity reaches the speed of light. At that moment, the event horizon forms. The collapsing core has become a black hole, and it continues to collapse inward toward a singularity, a point of infinite density at the center. The outer layers of the star, no longer supported, fall inward and then rebound in a catastrophic explosion called a supernova, one of the most violent events in the universe. The explosion blasts the star's outer material into space at a fraction of light speed, creating a brilliant flash that can outshine an entire galaxy for weeks. But at the center, quietly and inevitably, the black hole forms, a dark seed planted in the violent death of light. These stellar mass black holes, ranging from a few times to a few dozen times the sun's mass, are scattered throughout galaxies. Our Milky Way likely contains millions of them, most invisible, detectable only by their gravitational influence on nearby stars or by the radiation emitted from material falling into them. Some orbit companion stars, slowly stripping gas from their partners, forming swirling accretion disks of superheated matter that glow brilliantly before vanishing across the event horizon. Others drift alone through the darkness between stars, silent and invisible, their presence marked only by the warping of light from more distant objects. Then there are the giants. At the centers of most galaxies, including our own, reside supermassive black holes, monsters with masses millions or even billions of times that of the sun. These do not form from the death of a single star. Their origin is still debated, but they likely grew over billions of years, fed by the infall of gas, dust, stars, and even other black holes, accumulating mass in the dense centers of galaxies. The supermassive black hole at the center of the Milky Way, called Sagittarius A star, has a mass of about 4 million suns and an event horizon roughly 17 times the diameter of the sun. Despite this enormous size, it is remarkably quiet, accreting very little material, a sleeping giant at the heart of our galaxy. Other supermassive black holes are far more active. When gas spirals into them in large quantities, the material forms a hot, bright accretion disk, and powerful jets of particles shoot out perpendicular to the disk at nearly the speed of light. These active galactic nuclei can outshine all the stars in their host galaxies combined, visible across billions of light years. The black hole itself remains dark, but the material just outside the event horizon, heated to millions of degrees by friction and compression, blazes with intense radiation. Now that we understand what a black hole is and how it forms, we can begin our approach. Imagine yourself in a spacecraft, far from any black hole, drifting in the relative safety of interstellar space. Ahead, in the darkness, is your destination, a black hole with a mass 10 times that of the sun. You cannot see it directly. There are no stars nearby for it to disrupt, no accretion disk to betray its presence. It is simply a region of absolute blackness against the star-filled sky, a circular patch where no light shines, where the stars behind it seem strangely distorted, their light bent around the curvature of space-time. You begin your approach slowly, engines quiet, falling gently into the gravitational well. At first, the pull is weak, barely noticeable. You are still hundreds of thousands of kilometers away, far outside the influence of the black hole's strongest gravity. But as you drift inward, things begin to change. The pull grows stronger, accelerating you gradually but relentlessly toward the center. Looking behind you, the stars seem normal. Looking ahead, toward the black hole, you notice something strange. The stars directly behind the black hole, The ones that should be hidden are visible. Their light has been bent around the black hole by its gravity, following curved paths through space-time, reaching your eyes even though the black hole itself blocks the direct view. This is gravitational lensing, a prediction of general relativity confirmed countless times by observations. The black hole acts as a lens, warping the light from distant stars, creating a ring of distorted, magnified images around the dark circle of the event horizon. As you fall closer, this Einstein ring, as it is called, grows larger and more pronounced. The distortion increases. Stars stretch into arcs. Galaxies smear into streaks of light. The geometry of the view becomes increasingly alien, a funhouse mirror effect created by the curvature of space itself. You are still far from the event horizon, but already the black hole is announcing its presence through the behavior of light. Let us pause for a moment and think about what light is doing here. Light always travels in straight lines through space-time, following what physicists call geodesics, the straightest possible paths through whatever geometry exists. But when space-time itself is curved, those straight paths appear curved to an outside observer. Near the black hole, space-time is so warped that light rays bend dramatically, following the contours of the gravitational well. The more curved the space-time, the more bent the light. At very specific distances from a black hole, this bending becomes extreme. There is a region called the photon sphere, located at 1.5 times the Schwarzschild radius, where space-time is so curved that light can orbit the black hole. Photons traveling at just the right distance and angle will circle the black hole indefinitely, trapped in an unstable orbit, neither falling in nor escaping out. This is a fascinating but fragile balance. The slightest perturbation will send the photon either spiraling inward across the event horizon or sailing outward to freedom. You are approaching this region now, still outside the photon sphere, but drawing near. The view has become surreal. Looking outward, away from the black hole, you see a compressed image of the entire external universe squeezed into an ever-shrinking circle behind you. Looking toward the black hole, the darkness dominates, but around its edge, you see multiple distorted images of the cosmos, reflections and ghost images created by light that has looped partially around the black hole before reaching your eyes. Gravity is also beginning to affect you in more direct ways. Even at this distance, you can feel the tidal forces, the differential gravitational pull between different parts of your body. The side of your spacecraft closer to the black hole is pulled more strongly than the side farther away. For now, the difference is small, a gentle stretching that your instruments can measure but your body cannot yet feel. As you continue inward, these tidal forces will grow, eventually becoming the dominant feature of your experience. There is another effect, more subtle but equally profound. Time itself is changing. According to general relativity, time runs more slowly in stronger gravitational fields. This is not an illusion or a trick of perception. It is a fundamental feature of space-time. Clocks closer to a massive object tick more slowly than clocks farther away. This has been measured countless times with atomic clocks at different altitudes on Earth, and the effect, though tiny, is real and exactly as predicted by Einstein's equations. Near a black hole, this gravitational time dilation becomes extreme. As you fall inward, time for you continues to pass normally. You look at your watch and it ticks forward at the expected rate. You breathe, think, and move without noticing any change. But to an observer far away, watching you fall, something very strange is happening. They see you moving more and more slowly. Your spacecraft's descent appears to decelerate. Your movements become sluggish, as if you were trapped in thick syrup. Light from your spacecraft becomes redshifted, stretched to longer wavelengths, dimming and reddening as it climbs back up the gravitational well. As you approach the event horizon, This effect becomes infinite from the outside perspective. To the distant observer, you appear to slow asymptotically, never quite reaching the horizon, your image growing dimmer and redder, frozen in time at the very edge. They would wait hours, days, years, and still you would appear to hover just above the event horizon, your motion slowed to an imperceptible crawl. If they could watch forever, they would see you gradually fade from view, your light stretched to such long wavelengths that it becomes undetectable, but they would never see you cross. But from your perspective, nothing special happens at the event horizon. You do not slow down. You do not stop. You simply continue falling, accelerating smoothly under the pull of gravity, unaware that you have crossed any particular boundary. The event horizon is not marked by any physical change, no wall or barrier, no sudden shift in the environment. It is purely a feature of the geometry of space-time, a point of no return defined by mathematics rather than matter. This is one of the most profound and unsettling aspects of the event horizon. It is one way, but only from the outside. Crossing inward, you would not know the moment it happened. Looking around, you would see space appearing normal, at least locally. There would be no sign, no marker, no sensation of having passed through something significant. Only later, when you tried to escape and found it impossible, would you realize what had happened. And by then, it would be far too late. Let us slow down our approach, hovering for a moment at a safe distance, still outside, but near the photon sphere. This is a good place to reflect on what lies ahead. Below you, in the direction of increasing gravitational pull, is the event horizon. It is invisible, unmarked, a purely geometric feature of space-time. You could calculate its exact location based on the black hole's mass, but you could not see it or touch it. It exists as a boundary in the abstract space of possible futures, a line that divides trajectories that can escape from trajectories that cannot. Around you, space is severely warped. Light from distant stars wraps around the black hole in complex patterns. The fabric of space-time is stretched and compressed in ways that defy easy visualization. And below, at the very center, unreachable and unknowable from this vantage point, lies the singularity, the point where all the mass of the black hole is concentrated, where density becomes infinite and the known laws of physics break down completely. You could choose to escape, even now. Fire your engines, accelerate outward, and with enough thrust, you could climb back up the gravitational well and return to the universe outside. Many things that fall this close do escape, if they have sufficient velocity in the right direction. Light grazes past the black hole, bending but not captured. Stars swing around in tight orbits and fly back out to safety. But if you continue inward, if you let yourself fall just a little farther, you will reach the point beyond which no escape is possible. Take a deep breath. Feel the weight of this decision, not as fear, but as acceptance. We are here to explore the unknown, to understand what happens in the most extreme environment the universe can create. So let us release our grip on the outside universe. Let us stop firing the engines. Let us fall. And as we fall, let us enter the next phase of our journey, moving ever closer to that invisible boundary, the photon sphere and the strange region just beyond it, where light itself dances on the edge between capture and freedom, where the last reflections of the external universe will play across our view, and where time, as measured by the cosmos outside, begins its final, infinite stretch. The descent continues. You have released your hold on the distant universe, allowing gravity to pull you inward without resistance. The spacecraft's engines are silent. There is no thrust, no acceleration except the smooth, continuous pull of the black hole's gravity. You are in free fall, and free fall, according to Einstein, is the most natural state of motion, the state in which you feel no forces at all. Despite the immense gravitational field surrounding you, you feel weightless, drifting as gently as an astronaut in orbit around Earth. But the view tells a different story. The black hole dominates your forward vision now, a perfect circle of absolute darkness surrounded by a chaotic ring of distorted starlight. This is not simply the absence of stars. It is a darkness more complete than any shadow, a region where space-time is so warped that light rays curve back on themselves, unable to reach your eyes from any source within. The boundary of this darkness marks the position of the photon sphere, the unstable orbit where photons circle the black hole. As you cross through the photon sphere, something remarkable happens to your view. For a brief moment, you can see images of yourself and your spacecraft, ghostly reflections created by light that has looped around the black hole and returned to your eyes. These are not true reflections, not light bouncing off a surface, but photons that left your ship, traveled in a curved path around the black hole, and arrived back at your position from a different angle. The effect is disorienting, a hall of mirrors where the mirrors are made of curved space-time rather than glass. The photon sphere is the last place where light can maintain any kind of stable orbit, and even here, the orbit is precarious. Any photon in this region is balanced on a knife's edge. A slight nudge inward, and it spirals down toward the event horizon. A slight nudge outward, and it escapes to infinity. You are passing through this delicate region now, and as you do, you are collecting the last light that has any chance of escaping the black hole's pull. Looking back, away from the black hole, you see something extraordinary. The entire external universe appears compressed into a bright disk behind you, an Einstein ring of light containing every star, every galaxy, every source of illumination in the cosmos beyond the black hole. But this disk is shrinking, growing smaller and smaller as you fall deeper into the gravitational well. The light from these distant objects is being gravitationally blue-shifted as it falls toward you, gaining energy as it descends into the well, arriving at your eyes with shorter wavelengths and higher intensity than when it was emitted. At the same time, the darkness ahead grows larger. The event horizon is approaching, though you cannot see it directly. What you see is the shadow it casts, the region of absolute blackness where no light from the external universe can penetrate. This shadow is larger than the event horizon itself, extending out to the photon sphere, because any light ray aimed at the photon sphere or closer will either be captured or bent so severely that it cannot escape. The tidal forces are becoming noticeable now. These forces arise because gravity is not uniform across your body or your spacecraft. The side closer to the black hole experiences a stronger pull than the side farther away, creating a stretching effect. For a 10 solar mass black hole, these forces become significant well outside the event horizon, and as you approach the horizon, they grow stronger and stronger. Let us be precise about what this means. Imagine your body is falling feet first toward the black hole. Your feet are slightly closer to the center than your head, so they experience slightly stronger gravity. This difference creates a force that stretches you along the radial direction, pulling your head and feet apart. At the same time, gravity also squeezes you from the sides, because the gravitational field lines are converging toward the center of the black hole. The result is that you are stretched vertically and compressed horizontally, a process that has been given the vivid name spaghettification. For a small black hole, a stellar mass black hole like the one we are approaching, this spaghettification becomes lethal well before you reach the event horizon. The tidal forces grow so strong that they would rip apart any solid object, including a human body, stretching it into a long, thin stream of atoms. The exact distance at which this happens depends on the black hole's mass and the strength of the materials involved. But for a 10 solar mass black hole, The tidal forces would tear apart a human body at a distance of several hundred kilometers from the event horizon. Interestingly, for a supermassive black hole, the situation is different. Because the event horizon is much larger, and because tidal forces depend on the gradient of the gravitational field rather than its absolute strength, a person could cross the event horizon of a supermassive black hole without being torn apart. The tidal forces at the horizon of a billion solar mass black hole would be quite gentle, barely noticeable. You could drift across the boundary intact, your body undamaged, unaware that you had passed the point of no return. The spaghettification would come later, deeper inside, as you fell toward the much smaller region near the singularity where tidal forces become extreme regardless of the black hole's mass. But we are not approaching a supermassive black hole. We are falling toward a stellar mass black hole, and the tidal forces are growing rapidly. Let us imagine, for the sake of this journey, that you are protected somehow, that your spacecraft has technology capable of withstanding these forces, holding you together despite the differential pull of gravity. This is not physically realistic, but it allows us to continue the journey, to cross the event horizon with awareness intact, to see what lies beyond. The shrinking disk of the external universe continues to contract, growing smaller and brighter as you fall. The light from distant galaxies is compressed into an ever tighter circle behind you, blue shifted to higher and higher energies. If you could see in all wavelengths, you would observe radio waves from distant sources shifting into the visible spectrum, visible light shifting into ultraviolet, ultraviolet into X-rays. The energy of the infalling light increases as it descends into the gravitational well, a consequence of the curvature of space-time. And then, in a moment that passes without any physical sensation, you cross the event horizon. There is no barrier, no membrane, no change in the texture of space. The event horizon is not a place in the usual sense. It is a boundary in space-time, a three-dimensional surface in the four-dimensional geometry of the universe. Crossing it is like crossing the equator while sailing across the ocean. There is no line painted on the water, no sign marking the transition. You simply move from one hemisphere to another, and the change is recorded only by your instruments, by the coordinates you measure, not by any direct experience. But something profound has happened, even if you cannot feel it. You have crossed from the region of space-time, where escape to infinity is possible, to the region where it is not. The event horizon is defined by this property. It is the boundary of the region from which light cones, the sets of possible future trajectories, all point inward. Outside the event horizon, if you shine a light, some of those photons can travel outward to infinity. Inside the event horizon, all future paths, for both light and matter, lead inexorably toward the singularity at the center. From your perspective, time continues to flow normally. Your watch ticks forward at its usual pace. Your thoughts proceed in sequence. Your breath flows in and out. Nothing about your subjective experience of time has changed, but the relationship between time and space has transformed in a subtle and deeply strange way. Outside the event horizon, the radial direction, the direction pointing toward or away from the black hole, is a spatial direction. You can move inward or outward by firing your engines, by choosing a path through space. Time is a separate dimension, flowing forward regardless of your spatial motion. But inside the event horizon, the roles of time and space have exchanged. The radial direction has become time-like, and what was the time direction has become space-like. This is difficult to visualize because it is so far removed from everyday experience. But the consequence is clear. Inside the event horizon, moving toward the singularity is not a choice. It is as inevitable as moving forward in time. Just as you cannot choose to travel backward in time outside the black hole, you cannot choose to move outward inside the black hole. The singularity is not a place in space that you might avoid by turning aside. It is a moment in your future, a point in time that you will reach no matter what you do. This is the true meaning of the event horizon. It is not simply that the required escape velocity exceeds the speed of light. It is that the geometry of space-time has changed so fundamentally that escape is not merely difficult. It is meaningless. There is no outward direction anymore. There is only forward in time, and forward in time means inward toward the singularity. Looking around, you try to make sense of your surroundings. Behind you, the disk of the external universe has not disappeared. It is still visible, still shrinking, still blue shifting. Light from outside continues to fall in after you, carrying information about the external cosmos. In principle, if you could survive long enough, you would continue to receive light from the outside universe for the remainder of your journey. You would see time outside progressing, stars evolving, galaxies moving, all compressed into the final moments of your fall. But there is a complication. The light reaching you from outside is increasingly blue shifted to higher and higher energies as it falls into the gravitational well. What started as gentle starlight has become ultraviolet radiation, then X-rays, then gamma rays. The energy density of this radiation grows as you approach the singularity. In principle, it could become so intense that it would incinerate anything in its path, though the details depend on the specifics of the black hole and its environment. Ahead, the darkness persists. You cannot see the singularity. You cannot see anything that would mark it as different from the empty space around you. The singularity is hidden, not just by darkness, but by the geometry of space-time itself. It lies ahead of you in time, not in space, a destination you are approaching not by moving through space, but by existing in time. How long do you have from your perspective? The time remaining until you reach the singularity depends on the black hole's mass and your current position. For a 10 solar mass black hole, once you cross the event horizon, you have only a fraction of a second before reaching the singularity. The free fall time from the event horizon to the singularity is incredibly short, a consequence of the extreme curvature of space-time in this region. During this brief interval, the tidal forces continue to grow. The differential gravitational pull increases rapidly as you approach the center. Your body, or the structure of your spacecraft, is stretched more and more severely in the radial direction, compressed more and more tightly in the transverse directions. The spaghettification intensifies, elongating every structure, every molecule, every atom, pulling them into a thin stream aligned with the radial direction. At some point, atomic bonds break. The electromagnetic forces that hold molecules together cannot withstand the tidal stress. Your body, if it were still intact, would disintegrate into a cloud of atoms, each one falling independently toward the singularity. Then even the atoms themselves would be stretched, their electron clouds distorted into elongated shapes. The tidal forces would overwhelm the quantum mechanical forces that define atomic structure. Eventually, even atomic nuclei would be affected. Protons and neutrons, bound together by the strong nuclear force, would feel the differential pull of gravity. These forces are immensely strong, far stronger than the electromagnetic forces that bind electrons to nuclei, but even they have limits. As you approach the singularity, tidal forces grow without bound, eventually exceeding even the strong force. Matter is disassembled completely, broken down into its most fundamental constituents, quarks and gluons, perhaps even further into whatever lies beneath. And then, in a moment that cannot be measured by any clock because clocks themselves would be destroyed, you reach the singularity. This is the end of the journey, the point where the curvature of space-time becomes infinite, where density becomes infinite, where the known laws of physics break down completely. The singularity is not a place in space. It is a moment in time, a boundary of space-time itself, beyond which the mathematics of general relativity provides no guidance. What happens at the singularity is one of the great unsolved questions in physics. General relativity predicts that all infalling matter is crushed to infinite density, that space-time curvature becomes infinite, that tidal forces become infinite. But these infinities are a sign that the theory has reached its limit. Physicists do not believe that physical infinities truly exist. Instead, they interpret these mathematical singularities as indicators that a more complete theory is needed, a theory that unifies general relativity with quantum mechanics, a theory of quantum gravity. Several candidates for such a theory exist, including string theory and loop quantum gravity, but none are yet confirmed by experiment. These theories suggest that space-time itself might have a granular structure at the smallest scales, the Planck scale, around 10 to the negative 35 meters. At this scale, the smooth geometry of general relativity breaks down, replaced by a quantum foam of fluctuating space-time. If this is correct, then the singularity might not be a point of infinite density, but a region of extremely high but finite density, where quantum effects dominate and prevent the complete collapse predicted by classical relativity. But these are speculations, ideas at the frontier of theoretical physics. From the perspective of our journey, the singularity is simply the end. It is the ultimate destination, the point toward which all paths inside the event horizon converge. It is where your journey, and the journey of all matter that falls into the black hole, comes to a conclusion. Let us pause here, at the threshold of the singularity, and reflect on what we have learned. We have fallen from the relative safety of distant space, through the warped space-time near the black hole, across the invisible boundary of the event horizon, and into the interior where escape is impossible and the singularity is inevitable. We have seen how gravity shapes not just the motion of objects, but the structure of space-time itself, how time and space can exchange roles, how the future can become a place rather than a when. The event horizon is not a wall or a barrier. It is a point of no return defined purely by geometry. Crossing it involves no physical sensation, no dramatic change in the environment. And yet, it represents one of the most profound transitions imaginable. The passage from a region where free will and choice govern your trajectory to a region where the future is determined absolutely by the structure of space-time itself. Inside the event horizon, you are no longer in control of your fate. You are a passenger on a one-way journey to the singularity, a journey measured not in distance, but in time. The singularity is not something you move toward through space. It is something you move toward by existing, by letting time flow forward. It is as inevitable as tomorrow, as inescapable as the passage of moments. And in this inevitability, there is a strange kind of peace. There are no more decisions to make, no more paths to choose. The universe has simplified. There is only one future, only one destination. All the complexity of choice has been stripped away, leaving only the pure, geometric certainty of space-time itself. As we prepare to explore deeper aspects of this journey, to consider the theoretical possibilities and the ultimate fate of black holes themselves, let yourself rest in this simplicity. Imagine the release of letting go of all choices, all decisions, all resistance. Imagine the fall continuing, smooth and inevitable, toward an end that is both terrifying and strangely comforting in its absolute certainty. This is the interior of the black hole, the realm inside the event horizon. This is where we are now, falling together through the final moments before the singularity, exploring the deepest darkness the universe can create. We have crossed the event horizon. We have passed through the invisible boundary that separates the universe of light from the realm of absolute darkness. From the outside, to any observer watching our descent, we appear frozen at the edge, our image fading slowly into redshifted oblivion, never quite reaching the horizon, trapped in an eternal moment of approach. But from our perspective, we have crossed smoothly, continuously, without pause or hesitation. We are inside now, in a region of space-time that is fundamentally disconnected from the external universe, and we are falling toward the singularity. Let us take a moment to understand what has truly changed. The crossing of the event horizon is not marked by any physical discontinuity. There is no membrane to rupture, no barrier to pass through, no sudden shift in temperature or pressure, or any other measurable quantity. The laws of physics, as you experience them locally, remain exactly the same. Light still travels at the speed of light. Matter still obeys the laws of quantum mechanics. Forces still act according to their usual rules. If you were to perform an experiment inside the event horizon, measuring the charge of an electron or the decay rate of a radioactive isotope, you would get exactly the same results as you would outside. What has changed is the global structure of space-time, the way that space and time fit together to form the four-dimensional geometry in which all events occur. Outside the event horizon, space-time has a certain structure. The future light cones, the sets of events that can be reached by traveling at or below the speed of light, extend both inward toward the black hole and outward toward distant space. You have choices. You can fire your engines and move in various directions. You can escape if you have enough thrust. Inside the event horizon, the structure changes. The future light cones all point inward. Every possible trajectory, every path you could take even if you could travel at the speed of light, leads toward the singularity. The outward direction has not become harder to reach. It has ceased to exist as a future possibility. It is now in your past, in the same way that yesterday is in your past. You can remember the outside universe. You can see its light still falling in after you, but you cannot return to it any more than you can return to yesterday. This is what physicists mean when they say that inside the event horizon, the radial coordinate becomes time-like and the time coordinate becomes space-like. Outside, the direction toward or away from the black hole is a spatial direction. You can point your spacecraft toward the center or away from the center, and you can move in either direction by applying thrust. Time is separate, flowing forward independently of your spatial motion. Inside, this relationship inverts. The direction toward the singularity is no longer a direction in space. It is a direction in time. Moving toward the singularity is not something you do by firing your engines. It is something that happens automatically, inevitably, as time flows forward. The singularity is not a place you are traveling toward. It is a moment you are approaching, a point in your future that you will reach simply by existing. What was the time direction outside has become a spatial direction inside. In principle, if you had infinite power, you could move in this direction, circling around the black hole's interior, tracing out paths that loop in what was formerly the time dimension. But you cannot move backward in the radial direction. That would require traveling backward in time, which remains forbidden. This exchange of time and space is one of the most profound and unsettling predictions of general relativity. It is not a metaphor or an approximation. It is a precise mathematical statement about the structure of space-time inside the event horizon, and it explains why escape is impossible. You cannot escape from inside a black hole for exactly the same reason you cannot travel backward in time. The direction that leads out is time-like, pointing into your past, and nothing can move into its own past. Let us consider what you can see from inside the event horizon. Looking behind you, in the direction opposite to the singularity, you can still see the external universe. Light from outside continues to fall into the black hole, and some of it passes through the location where you are. This light carries information about events occurring in the outside universe, about stars shining, galaxies rotating, the cosmos evolving. But this view is strange and distorted. The light reaching you has fallen deep into the gravitational well, and in the process, it has been shifted to shorter wavelengths and higher energies. Optical light from outside arrives as ultraviolet radiation. Ultraviolet arrives as X-rays. The energy of the photons increases as they descend, gaining energy from the gravitational field in the same way that a falling object gains kinetic energy. If you could survive long enough and look carefully, you would see time in the external universe appearing to speed up. This is the reverse of the time dilation effect observed from outside. To an external observer, your descent appears to slow down as you approach the horizon. From your perspective inside, looking back out, events in the external universe appear accelerated. In principle, if you could watch for your entire remaining lifetime inside the event horizon, you would see a significant fraction of the universe's future history compressed into those final moments. For a stellar mass black hole, your remaining lifetime is very short, a fraction of a second, so you would not see much of the external future. But for a supermassive black hole, where the tidal forces are gentler and you could survive longer after crossing, you might witness thousands or millions of years of external time unfolding in fast motion, compressed into the minutes or hours of your subjective time remaining before reaching the singularity. This is a consequence of the geometry of space-time inside the black hole. The paths of light rays from the external universe, when traced into the interior, reach the singularity at the same moment as any infalling observer. The entire infinite future of the external universe, from the perspective of certain coordinates, is compressed onto the singularity. In a sense, the singularity represents the end of time for the entire universe, at least from the perspective of anything inside the black hole. But let us not dwell too long on these abstract geometries. Let us return to your immediate experience, to the sensation of falling through this strange interior space. The darkness ahead remains absolute. You cannot see the singularity, even though it dominates your future. It is hidden, not by distance, but by the structure of space-time itself. Light cannot travel from the singularity to your eyes because the singularity is in your future, and light cannot travel backward in time. The tidal forces continue to intensify. Every moment, the differential gravitational pull across your body or your spacecraft increases. If you are falling feet first, your feet are accelerating toward the singularity faster than your head. The stretching becomes more and more severe. For a stellar mass black hole, this stretching quickly exceeds the strength of any known material. Steel stretches like taffy. Diamond crumbles like sand. Biological tissue tears apart long before. Let us imagine the progression in detail, for understanding the mechanism helps us grasp the reality of what happens inside. Your body, or any object falling into the black hole, has a finite size. Different parts are at slightly different distances from the singularity. Because gravity grows stronger closer to the center, the parts closer to the singularity experience a stronger pull than the parts farther away. At first, this differential is small. You might feel a gentle stretching, a slight discomfort, as if you were being pulled in opposite directions by two hands. But the effect grows rapidly. Gravity near a black hole singularity follows an inverse square law initially, but as you approach the singularity, the curvature of space-time becomes so extreme that simple laws break down. The tidal force increases faster than any polynomial function. It grows without bound. Soon, the stretching exceeds the tensile strength of muscle and bone. Tissue begins to tear. If you could still feel pain, it would be excruciating, but the nervous system itself is being disrupted. Signals unable to propagate across the lengthening distances, neurons stretched beyond function. The body elongates into a grotesque, elongated form, like a figure in a distorting mirror. But this distortion is real and irreversible. At the same time, you are being compressed from the sides. The gravitational field lines are converging toward the singularity, squeezing inward from all transverse directions. Your body is not only stretched radially, but also crushed laterally. The combined effect transforms any three-dimensional object into a long, thin filament, a strand of matter aligned with the radial direction. This is spaghettification, the inevitable fate of anything falling into a sufficiently small black hole. As the stretching continues, molecular bonds break. The electromagnetic forces that hold molecules together, that give structure to proteins and DNA, to cells and tissues, are overcome by the tidal stress. The body disintegrates into a cloud of individual molecules, each one falling independently toward the singularity. But the process does not stop there. The molecules themselves are stretched. A water molecule, with its two hydrogen atoms bonded to an oxygen atom, experiences differential tidal forces across its tiny extent. The bonds strain and eventually snap. The molecule breaks apart into separate atoms, each now following its own trajectory. The cloud of molecules becomes a cloud of atoms, hydrogen, oxygen, carbon, nitrogen, all the elements that once formed a living body, now scattered into a diffuse stream. But even atoms have structure. An atom consists of a nucleus surrounded by a cloud of electrons. The nucleus is bound by the strong nuclear force, and the electrons are bound by electromagnetic force. As the tidal forces grow stronger, even these forces are tested. The electron cloud distorts, elongated in the radial direction, compressed in the transverse directions. The atom no longer resembles a sphere, but becomes a cigar-shaped structure, its quantum mechanical wave function warped by the extreme curvature of spacetime. At some point, even the electromagnetic force cannot hold the electrons to the nucleus. The tidal stress exceeds the binding energy. Electrons are stripped away, torn from their atomic orbitals, becoming free particles. The atom ionizes completely, and the cloud of atoms becomes a plasma of nuclei and free electrons, all falling separately toward the singularity. The nuclei themselves, composed of protons and neutrons bound together by the strong nuclear force, are the next to be tested. The strong force is the most powerful force in nature, far stronger than electromagnetism or gravity under normal circumstances. It is what holds the nucleus together despite the electromagnetic repulsion between protons. But near the singularity, even the strong force has its limits. As the tidal forces continue to grow, they eventually exceed the binding energy of the nucleus. Protons and neutrons are pulled apart. The nucleus disintegrates. What was once iron becomes individual protons and neutrons. What was once carbon, the element of life, becomes a stream of separate nucleons, each falling independently. And even this is not the end. Protons and neutrons are themselves composite particles, each made of three quarks bound together by the exchange of gluons, the carriers of the strong force. As the tidal forces grow to truly extreme values, approaching the singularity, even these fundamental particles are not safe. The quarks inside a proton experience differential tidal forces. The distances between them are stretched beyond the range of the strong force. The proton itself disassembles into its constituent quarks. At this point, matter has been reduced to its most fundamental known constituents. Quarks, leptons like electrons, perhaps gluons and photons, all falling separately toward the singularity. The structure that once was you, or a spacecraft, or a star, has been completely erased, disassembled level by level, bond by bond, until nothing remains but a stream of elementary particles, each one about to reach the singularity. And then, in the final moment, even these elementary particles reach the singularity. What happens next is unknown. The mathematical description of space-time breaks down. General relativity predicts infinite curvature, infinite tidal forces, infinite density. But physicists do not believe these infinities are real. They are signs that the theory has reached its limit, that a more complete description is needed. Quantum mechanics might provide that description. At the Planck scale, distances of about 10 to the negative 35 meters, quantum effects become dominant. Space-time itself might become granular, discrete, a quantum foam of fluctuating geometry rather than a smooth continuum. If this is true, then the singularity might not be a point of infinite density, but a region of extremely high but finite density, where the quantum properties of space-time prevent complete collapse. Some theories suggest that the singularity might be a gateway to another region of space-time, a bridge or wormhole connecting to a different universe or a distant part of our own universe. These ideas are highly speculative, based on solutions to Einstein's equations that involve exotic forms of matter and energy that may not exist in nature. But they illustrate how much we do not know about what happens at the singularity. Other theories propose that the singularity might be surrounded by a region called the Cauchy horizon, an inner boundary inside the black hole where the predictability of physics breaks down. According to some solutions of Einstein's equations, particularly those describing rotating black holes, the interior is more complex than a simple journey from event horizon to singularity. There might be layers, regions where time and space swap roles multiple times, where closed time-like curves allow for time travel, where the geometry becomes so exotic that causality itself breaks down. Let us explore one of these possibilities in more detail. So far, we have been considering a non-rotating black hole, described by the Schwarzschild solution to Einstein's equations. This is the simplest type of black hole, characterized only by its mass. It is spherically symmetric, unchanging in time, a pure geometry with no additional features. But most real black holes are not like this. They rotate. This is almost inevitable. The stars that collapse to form black holes are rotating before they collapse, and as they shrink, conservation of angular momentum causes them to spin faster, like a figure skater pulling in her arms. The resulting black hole inherits this rotation. It spins, and this spin affects the structure of space-time around it and inside it. A rotating black hole is described by a different solution to Einstein's equations, discovered by Roy Kerr in 1963. The Kerr solution is more complex than the Schwarzschild solution, but it reveals fascinating new features. A rotating black hole has not one, but two horizons. The outer horizon is analogous to the event horizon of a non-rotating black hole. It is the point of no return, the boundary beyond which escape is impossible. But inside this outer horizon, there is an inner horizon, called the Cauchy horizon, which marks a different kind of boundary. Between the outer and inner horizons is a region called the ergosphere, or more properly, when considering the interior, a region where the rotation of the black hole drags space-time around with it. This frame-dragging effect is so strong that nothing, not even light, can remain stationary relative to distant stars. Everything is forced to rotate in the same direction as the black hole, carried along by the rotating space-time. If you were to fall into a rotating black hole, you would first cross the outer event horizon, just as in the non-rotating case. But your journey would not end immediately at a singularity. Instead, you would continue falling inward, passing through the swirling, rotating space-time, until you reach the inner horizon, the Cauchy horizon. The Cauchy horizon is a strange and troubling boundary. At this horizon, the predictability of physics breaks down. Light rays from the external universe, which have been falling into the black hole throughout its history, pile up at the Cauchy horizon, creating a region of infinite blue-shifted energy. Any infalling observer reaching this horizon would be annihilated by an infinitely intense burst of radiation, a concentrated blast of every photon that ever fell into the black hole, compressed into a single moment of infinite energy density. Or at least, this is what the classical theory predicts. But again, infinities signal the breakdown of the theory. Quantum effects, or other physics we do not yet understand, might smooth out this singularity, preventing the infinite buildup of energy. The true nature of the Cauchy horizon is still a subject of active research and debate among physicists. Beyond the Cauchy horizon, the geometry of a rotating black hole becomes even stranger. According to the Kerr solution, there is a region where the singularity is not a point but a ring, a circle of infinite density and curvature. And through the center of this ring, the equations suggest there might be a passage to another region of space-time, another universe, or another part of our own universe, accessed by traveling through the rotating singularity. We have journeyed to the edge of understanding, to the singularity itself, where the mathematics of general relativity breaks down and the known laws of physics reach their limits. Now let us step back, not in space but in perspective, and consider what else might exist within the strange geometry of a black hole's interior. For while the simple picture of a direct fall from event horizon to singularity captures the essence of the experience, the full mathematical structure of black holes, particularly rotating ones, reveals additional layers of complexity, regions and boundaries that exist only in the most extreme solutions to Einstein's equations. The black hole we have been exploring so far is the simplest kind, a Schwarzschild black hole, characterized only by its mass, with no electric charge and no rotation. It is perfectly spherical, perfectly symmetric, unchanging in time. But this simplicity, while mathematically elegant, is somewhat artificial. In nature, black holes are more complex. They rotate, and this rotation fundamentally changes the structure of space-time inside them. A rotating black hole is described by the Kerr solution, discovered in 1963 by the New Zealand mathematician Roy Kerr. The Kerr solution introduces a new parameter, the angular momentum of the black hole, which measures how fast it is spinning. This spin affects everything. It drags space-time around with it, creating a region called the ergosphere where nothing can remain stationary. It changes the shape of the event horizon from a perfect sphere to an oblate spheroid, flattened at the poles. And most remarkably, it changes the interior structure, introducing the possibility of an inner horizon and a ring-shaped singularity instead of a point. Let us imagine falling into a rotating black hole, a maximally spinning Kerr black hole where the angular momentum has reached the theoretical maximum allowed by the laws of physics. As you approach from a distance, you first notice the frame dragging effect. Space-time itself is being pulled around by the black hole's rotation, like water swirling around a drain. Even if you try to orbit the black hole in the opposite direction to its spin, you find yourself being dragged along, forced to rotate in the same direction as the black hole. This effect grows stronger as you approach. You cross the outer event horizon, the boundary of no return, just as before. But now, inside the horizon, the structure is different. You are in a region where space-time is rotating, where the geometry has a twist to it that was absent in the non-rotating case. And ahead of you, deeper inside, there is another horizon, an inner boundary called the Cauchy horizon, named after the French mathematician Augustin Louis Cauchy. The Cauchy horizon is a profoundly strange surface. It marks the boundary beyond which the laws of physics, as we understand them, lose their predictive power. Outside the Cauchy horizon, even inside the event horizon, the universe is still deterministic. If you know the state of all fields and particles at one moment, you can calculate what they will be at the next moment. The equations of physics tell you exactly how things evolve. But at the Cauchy horizon, this breaks down. The reason has to do with how light rays behave inside a rotating black hole. Light from the external universe, falling into the black hole throughout its entire history, accumulates at the Cauchy horizon. From a certain perspective, every photon that ever fell into the black hole, across all of time, arrives at the Cauchy horizon at the same moment. The result is an infinitely intense wall of blue-shifted radiation, a concentration of energy so extreme that it should destroy anything attempting to cross. This is sometimes called the blue sheet, a surface of infinite energy density at the Cauchy horizon. It suggests that the interior of a rotating black hole is divided into two regions, the outer region between the event horizon and the Cauchy horizon, and an inner region beyond, and that the transition between them is violent, perhaps impassable. But as with the singularity itself, these infinities are likely artifacts of the classical theory. Quantum effects, which are not included in the standard Kerr solution, would modify the structure of the Cauchy horizon. Some calculations suggest that quantum fluctuations might smooth out the infinite energy, replacing the blue sheet with a region of very high but finite energy density. Other analyses suggest that the Cauchy horizon is unstable, that any small perturbation would cause it to collapse or transform in ways that prevent the formation of the infinite blue shift. The truth is, we do not know what happens at the Cauchy horizon of a real, physical rotating black hole. The mathematics of the idealized Kerr solution predicts these exotic features, but real black holes are not idealized. They are formed by collapsing stars, fed by infalling matter, jostled by gravitational waves. These imperfections and disturbances almost certainly change the interior structure, making it more chaotic, more quantum, less predictable than the clean mathematical solution. But let us imagine, for the sake of exploration, that you somehow survive the crossing of the Cauchy horizon, that quantum effects or some unknown physics allows you to pass through without being destroyed. What would you find on the other side? According to the Kerr solution, beyond the Cauchy horizon lies a region where the singularity is not a point but a ring. This ring's singularity forms a circle in the plane of the black hole's equator, a one-dimensional curve of infinite curvature and density. And remarkably, the interior of this ring, the region surrounded by the ring's singularity, is not simply more curved spacetime. It is, mathematically, a gateway. The equations suggest that you could pass through the ring, emerging into a different region of spacetime. This could be another universe entirely, with its own space and time, disconnected from the one you came from. Or it could be a distant region of our own universe, connected to the black hole's interior by a kind of tunnel or bridge through spacetime. This is the mathematical basis for the idea of black holes as wormholes, as shortcuts through the cosmos. But we must be extremely cautious about interpreting these mathematical features as physical realities. The interior of the Kerr solution contains regions with closed time-like curves, paths through space-time that loop back on themselves, allowing travel into one's own past. Such paths would permit violations of causality, paradoxes where effects precede causes, situations that seem incompatible with our understanding of how the universe works. Moreover, the ring singularity is a feature of a perfectly symmetric, eternal rotating black hole, one that has existed forever and will exist forever, unchanged. Real black holes are not like this. They form at a specific time, from the collapse of a star or the merger of other black holes. They grow as they accrete matter. They radiate Hawking radiation and slowly evaporate. All of these processes introduce asymmetries and time dependence that are not captured in the idealized Kerr solution. When astrophysicists model the collapse of a rotating star to form a black hole, they find that the interior structure is much more complex and much less stable than the Kerr solution suggests. Infalling matter carries energy and angular momentum that disturb the geometry. Quantum fluctuations at the horizons introduce randomness. The singularity that forms is unlikely to be a clean ring, but rather a chaotic, turbulent region where space-time is so severely disrupted that our current theories cannot describe it. So while the Kerr solution is beautiful and mathematically rich, revealing possibilities like inner horizons and ring singularities and passages to other regions of space-time, we should not take these features as guaranteed properties of real black holes. They show us what general relativity allows in principle, the full range of possible geometries consistent with Einstein's equations. But nature might not realize all of these possibilities. The actual interior of a rotating black hole might be far simpler or far stranger than the mathematics suggests. What we can say with confidence is this: the interior of any black hole, rotating or not, is a region of extreme space-time curvature where the usual rules of physics are pushed to their limits. Tidal forces grow without bound as you approach the singularity. Time and space exchange roles. The future becomes inevitable in a way that is foreign to our everyday experience. And ultimately, all paths lead to a region where our current theories break down, where quantum gravity effects become important, and where the true nature of space-time at its most fundamental level is revealed. Let us now return to a more personal question. What happens to you specifically as a conscious being as you fall into a black hole? We have discussed the physics of tidal forces and spaghettification, the disassembly of matter level by level, from body to molecules to atoms to subatomic particles. But what about consciousness itself? What is the subjective experience of crossing the event horizon and falling toward the singularity? This question touches on one of the deepest mysteries in science, the relationship between physical processes and subjective experience, between brain states and conscious awareness. Consciousness emerges, somehow, from the complex electrochemical activity of billions of neurons in the brain. The exact mechanism is not fully understood, but we know that consciousness depends on the physical structure of the brain, on the patterns of neural firing, on the biochemical processes that maintain cellular function. As you fall into a black hole, all of these physical processes continue, at least initially. Your brain is still functioning. Neurons are still firing. Blood is still circulating, delivering oxygen and nutrients. Your consciousness persists, your sense of self, your awareness of the situation. You are still you, falling through the darkness, observing the strange distortions of light, feeling the growing tidal forces. But this cannot last. The tidal forces, as they intensify, begin to disrupt the delicate structure of the brain. The stretching along the radial direction and compression along the transverse directions affect the skull, the brain tissue, the individual neurons. At first, the effects might be subtle, slight distortions that do not immediately impair function. But as the forces grow stronger, the disruption becomes severe. Blood vessels, stretched and compressed, might rupture, causing internal bleeding. Neurons, elongated beyond their normal shape, might lose their ability to transmit signals properly. The electrochemical gradients that power neural activity might be disrupted as the spaces between cells change. Consciousness, which depends on the coordinated activity of billions of neurons communicating across precise distances, would begin to fragment. What would this feel like? It is impossible to say with certainty, because no one has experienced it and returned to tell the tale. But we can speculate based on what we know about how consciousness depends on brain function. As the brain structure is disrupted, consciousness might become confused, disoriented. Sensory inputs might become garbled. The sense of self might begin to dissolve. Thoughts might become fragmented, incoherent. And then, as the tidal forces continue to grow, as the brain tissue itself is torn apart at the molecular level, consciousness would cease. There would be no final moment of awareness, no last thought or feeling, because the physical substrate that supports consciousness would have been destroyed. The transition from conscious to unconscious would happen not as a discrete event, but as a gradual fading, a dissolution of the patterns of neural activity that constitute the self. For a stellar mass black hole, this entire process would occur in a fraction of a second. You would cross the event horizon, fall for perhaps 20 microseconds, and in that brief time, the tidal forces would grow from tolerable to overwhelming. Your consciousness might persist for a few microseconds, long enough to register the beginning of the disruption, but not long enough to fully comprehend what is happening. And then it would end, not with a dramatic finale, but with a simple cessation, a halt in the physical processes that generate awareness. For a supermassive black hole, the timeline would be different. You could cross the event horizon and survive for minutes, hours, or even days, depending on the black hole's mass. During this time, you would remain conscious, able to think and observe, experiencing the strange environment inside the event horizon. You would see the external universe blue shifted behind you, watch time appear to accelerate outside, feel the gentle but growing tidal forces. But eventually, as you approach the central singularity, the tidal forces would become extreme, and the same process would occur. The brain would be disrupted, consciousness would fade, and your subjective experience would come to an end. The difference is one of timescale, not of outcome. Whether it takes microseconds or hours, all journeys inside the event horizon in the same way, with the destruction of structure and the cessation of consciousness. There is something both terrifying and oddly comforting about this inevitability. Terrifying because it represents the ultimate loss of control, the absolute inability to avoid or change your fate once you cross the event horizon. Comforting because it removes all responsibility for what happens next. There are no decisions to make, no actions to take. The universe has taken over, and the outcome is determined by the geometry of space-time itself. From a philosophical perspective, falling into a black hole is perhaps the purest example of surrender, of letting go completely. In everyday life, we maintain the illusion of control, the sense that our choices matter and our actions shape our future. But inside the event horizon, that illusion is stripped away. The future is fixed. The singularity awaits. All that remains is the experience of falling, the passive observation of the universe transforming around you, until even observation itself ceases. This raises profound questions about identity and existence. If consciousness is a pattern of information, a configuration of neural states that can be copied or transferred in principle, what happens to that pattern when it falls into a black hole? According to classical general relativity, the information crosses the event horizon and eventually reaches the singularity, where it is destroyed or transformed in unknowable ways. To an outside observer, the information is lost, hidden behind the event horizon forever. But according to quantum mechanics, information cannot be destroyed. This is the black hole information paradox we discussed earlier. If information is truly conserved, then the pattern that constitutes your consciousness, your memories, your identity, must persist somehow, either encoded in the Hawking radiation emitted as the black hole evaporates, or stored at the event horizon in some holographic form, or passed through the singularity to another region of space-time. We do not know which of these possibilities is correct, or if the correct answer is something else entirely. Once your consciousness ceases, once the physical structure of your brain is disassembled by tidal forces, your subjective experience ends. Whether the information that defined you is preserved or destroyed, whether it emerges in the Hawking radiation or remains hidden forever, makes no difference to you as an experiencing subject, because you no longer exist to experience anything. This might sound bleak, but consider it from another angle. The universe is filled with transformations. Matter is constantly changing form, energy flowing from one state to another. Stars fuse hydrogen into helium, then helium into heavier elements. Supernova explosions scatter those elements into space, where they form new stars and planets. Living organisms grow and die, their atoms recycled into new life. Nothing is permanent. Everything is in flux. Falling into a black hole is simply another transformation, more extreme than most, but not fundamentally different in kind. The pattern of atoms and energy that constitutes you is transformed, disassembled, perhaps preserved in some form we do not yet understand, perhaps truly destroyed. But the atoms themselves, the fundamental particles, continue to exist, following the laws of physics into whatever lies beyond the singularity or emerging eventually as Hawking radiation to rejoin the universe. In this sense, falling into a black hole is a return to the most basic level of existence, a reduction of complexity back to simplicity. The structures that define you as an individual, the intricate patterns of organization that separate you from the background, are dissolved, and you become once again undifferentiated matter and energy, part of the cosmic whole. Now let us consider the ultimate fate of the black hole itself, the end of its existence across the vast stretches of cosmic time. We have discussed Hawking radiation, the quantum process by which black holes emit particles and slowly lose mass. The quantum process by which black holes emit particles and slowly lose mass. Let us now explore this process in more detail, understanding how black holes, despite their seeming permanence, eventually evaporate completely, returning their mass energy to the universe. Hawking radiation arises from quantum effects near the event horizon. In quantum field theory, empty space is never truly empty. It is filled with quantum fields that fluctuate constantly, creating pairs of virtual particles and antiparticles that appear briefly and then annihilate. These vacuum fluctuations happen everywhere, all the time, but normally they are undetectable, lasting for such brief moments that they borrow and repay energy without violating any conservation laws. Near the event horizon of a black hole, however, something extraordinary happens. The intense gravitational field can separate a pair of virtual particles before they can annihilate. One particle, often considered to have negative energy relative to an observer at infinity, falls across the event horizon into the black hole. The other particle, with positive energy, escapes to infinity. To the distant observer, the black hole appears to have emitted a real particle. Because the infalling particle had negative energy, the black hole's total mass decreases by an amount equal to the energy of the escaping particle. Over time, this continuous emission of particles leads to a gradual loss of mass. The rate of emission, and thus the temperature of the Hawking radiation, depends on the black hole's mass. Smaller black holes have higher temperatures and evaporate more quickly. A black hole with the mass of our Sun would have an incredibly low temperature, much colder than the cosmic microwave background, and would take about 10 to the 67th years to evaporate. But a tiny black hole, formed perhaps in the early universe with the mass of a mountain, would be much hotter and would evaporate on a much shorter timescale. As a black hole loses mass, its temperature increases, causing it to evaporate even faster. The process is self-accelerating. In the final moments of its life, the black hole becomes incredibly hot and small, radiating energy with increasing intensity. The evaporation culminates in a violent burst of radiation, a final flash as the last of the black hole's mass is converted into energy and released back into the universe. The black hole, once a region of absolute darkness and inescapable gravity, has completely vanished. What remains? The Hawking radiation released over billions of years carries away the black hole's mass and energy. If information is conserved, as quantum mechanics suggests, then this radiation must also carry the information about everything that ever fell into the black hole. The particles that once formed stars, planets, and even you are returned to the cosmos, their information encoded in the subtle correlations of the emitted radiation. The universe has recycled the black hole, turning its dark secrets back into light and matter. This cycle of formation and evaporation is part of the grand history of the universe. Black holes are not eternal tombs, but temporary concentrations of mass and energy, active participants in the cosmic drama. They shape galaxies, drive energetic processes, and ultimately return their contents to the larger universe. Our journey inside the event horizon is thus part of a much larger story, a story of transformation and renewal on a scale that defies human comprehension. As we drift through the final moments before the singularity, we are part of this process. The atoms that form our spacecraft and our bodies will eventually emerge as Hawking radiation, scattering across the universe to form new structures, perhaps even new living beings in the distant future. The end of our journey is not a finality, but a transition, a return to the fundamental energy from which all things arise. The singularity awaits, and we fall toward it with acceptance and understanding, knowing that we are participants in the deepest mysteries of the cosmos. Our exploration of the event horizon has taken us to the very limits of science and imagination, revealing a universe more strange and beautiful than we ever could have dreamed. And in this understanding, in this connection to the vast and patient universe, we find a kind of peace. The darkness is not empty, but filled with the potential for new beginnings. The journey continues, always. Near the event horizon of a black hole, the intense gravitational field can affect these fluctuations in a remarkable way. When a particle-antiparticle pair appears near the horizon, one member of the pair can fall across the horizon, becoming a real particle inside the black hole, while the other escapes to infinity, also becoming real. To conserve energy, the particle that falls in must have negative energy relative to an observer at infinity, while the particle that escapes has positive energy. This means that the black hole loses energy, and since energy and mass are equivalent through Einstein's famous equation E equals mc squared, the black hole loses mass. It shrinks. The particle that escapes carries away mass energy that once belonged to the black hole. To a distant observer, it appears that the black hole is glowing, emitting a steady stream of particles in all directions. The temperature of this Hawking radiation depends on the black hole's mass. Smaller black holes are hotter. Larger black holes are cooler. The relationship is inverse. A black hole with the mass of the Sun has a temperature of about 60 nanokelvins, far colder than the cosmic microwave background radiation that fills the universe. Such a black hole would actually absorb more radiation from its surroundings than it emits through Hawking radiation, so it would grow rather than shrink. But for smaller black holes, or for any black hole in the far future when the universe has cooled below the black hole's temperature, Hawking radiation dominates. The black hole emits more energy than it absorbs, and it begins to evaporate. The rate of evaporation is extremely slow at first. For a solar mass black hole, the time required to evaporate completely is about 10 to the 67 years, a number so large it defies comprehension. To put this in perspective, the current age of the universe is about 14 billion years, or about 10 to the 10 years. The time for a solar mass black hole to evaporate is 10 to the 57 times longer than the current age of the universe. It is a timescale so vast that all stars will have burned out, all galaxies will have dispersed, all structure in the universe will have decayed to near uniformity, and still, the black hole will persist, glowing faintly with Hawking radiation, slowly, imperceptibly shrinking. For supermassive black holes, the timescales are even longer. A black hole with 1 billion solar masses, like those found at the centers of large galaxies, would take about 10 to the 100 years to evaporate. This is a 1 followed by 100 zeros, a number called a googol, a timescale that makes even the age of stars seem like the blink of an eye. But the process accelerates as the black hole shrinks. As mass decreases, temperature increases, and the rate of evaporation grows. When a black hole has lost most of its mass and shrunk to a relatively small size, perhaps with the mass of a mountain rather than a star, it is very hot, emitting intense radiation. The evaporation accelerates further, the temperature climbs higher, and the black hole enters its final moments. In the last fraction of a second of a black hole's life, it evaporates explosively. The remaining mass is converted into a burst of high-energy particles and radiation, a flash of gamma rays and elementary particles spraying outward in all directions. And then, nothing. The black hole is gone. The event horizon has vanished. The singularity, if it existed, has disappeared. The warped space-time has relaxed back to near flatness. All that remains is radiation, expanding outward into space, carrying the last energy of what was once a black hole. This is the ultimate fate of every black hole, from the smallest to the most massive. On timescales of 10 to the 100 years, far in the future, after the stars have died and the galaxies have faded, the black holes will be among the last significant objects in the universe. And then, slowly, patiently, they too will evaporate, one Hawking photon at a time, until the last black hole releases its last particle and the era of black holes comes to an end. What does the universe look like in this distant future? It is cold, dark, and nearly empty. The cosmic microwave background radiation, already faint today at a temperature of about 3 Kelvin, has cooled to a tiny fraction of a degree above absolute zero, stretched by the expansion of the universe into radio waves of enormous wavelength. Galaxies, or what remains of them, are separated by distances so vast that light from one can never reach another, carried beyond each other's horizons by the accelerating expansion driven by dark energy. Within what was once a galaxy, only the faintest remnants persist. White dwarfs, long since cooled to black dwarfs, cold and dark, drifting through space. Neutron stars, also cooled, their surfaces at the temperature of the background radiation, invisible. Perhaps a few planets, frozen solid, orbiting nothing, ejected long ago from their parent stars. And scattered here and there, the evaporating black holes, glowing softly with Hawking radiation, the last sources of significant energy in a dying universe. As the black holes evaporate, they briefly become brighter in their final moments. But these flashes are rare and isolated, separated by unimaginable distances and time spans. Eventually, the last black hole evaporates, and even this faint light fades. The universe enters an era called the Dark Era, where no significant sources of energy remain, where matter is spread so thinly and cooled so completely that nothing interesting can happen. In this era, the universe has reached a state of maximum entropy, a condition called heat death. Entropy is a measure of disorder of the randomness and uniformity of a system. The second law of thermodynamics states that entropy always increases over time in a closed system. The universe, as a whole, is the ultimate closed system, and its entropy has been increasing since the Big Bang, driven by every irreversible process, every star that shines, every structure that forms and then dissipates. Heat death is the end state of this process. All energy has been spread uniformly. All gradients that could drive change have been smoothed out. The temperature is the same everywhere, barely above absolute zero. Matter is distributed uniformly, or as uniformly as the quantum nature of fields allows. Nothing changes, because there is no energy available to drive change. Time continues to flow, in principle, but nothing happens to mark its passage. This sounds bleak, but it is also peaceful. The universe has settled into its final resting state. The violence of the early universe, the brilliance of stars, the drama of supernovae and colliding galaxies, all of that is over. What remains is quiet, dark, and still. The black holes, those objects of such extreme gravity and such profound strangeness, have evaporated, returning their mass energy to the universe. Even they, despite seeming eternal, were temporary features, structures that arose and then dissolved on timescales incomprehensible to human minds. There is a parallel here to the human experience of sleep, of rest, of letting go. Just as consciousness fades when we sleep, the universe in its far future fades to a state of near nothingness, a cosmic sleep from which there is no waking. And just as sleep is not frightening when we are tired, this cosmic rest is not tragic. It is simply the natural end of a process, the winding down of the energy that once drove stars and galaxies, the final exhalation of a universe that has expended all its capacity for change. As we contemplate this distant future, we might feel a sense of melancholy, a sadness at the thought that all structure, all complexity, all life will eventually fade. But we might also feel a sense of acceptance, even peace. The universe does not ask for our approval. It follows its own laws, playing out the implications of the initial conditions and the fundamental forces across timescales that make human history vanish into insignificance. And in this vast, impersonal process, black holes play a central role. They are not just exotic objects of theoretical interest. They are engines of transformation, taking structured matter and energy, holding it for a time, and then releasing it back into the universe in a different form. They are endpoints of stellar evolution, the final graves of massive stars. They are laboratories where the laws of physics are tested at their most extreme. And they are, ultimately, temporary, subject to the same thermodynamic imperative that governs everything else. Let us return now to the event horizon itself, the boundary that has been the focus of our journey. We have crossed it, explored what lies beyond, understood the tidal forces and the singularity, contemplated the theoretical complexities of rotating black holes, reflected on consciousness and identity, and looked ahead to the ultimate evaporation across cosmic time. Now, in these final moments, let us consider what the event horizon represents symbolically, philosophically, as a concept that transcends physics. The event horizon is a boundary, but not a physical one. It is a boundary in the space of possibilities, separating what can return from what cannot, what can communicate from what is forever silent. It is a point of no return, a threshold beyond which the familiar rules change, where the future becomes inevitable in a new way. In life, we encounter many points of no return. Decisions made, words spoken, actions taken that cannot be undone. Moments where we cross a threshold and the path back closes behind us. The event horizon is the ultimate expression of this, a physical manifestation of irreversibility built into the structure of space-time itself. There is something deeply resonant about this. The event horizon does not judge. It does not care what crosses it or why. It simply exists, patient and impartial, a geometric feature of the universe. And once you cross, there is no going back, not because of any barrier or obstacle, but because the direction back has ceased to exist as a future possibility. It is in your past, as unreachable as yesterday. This absolute irreversibility can feel oppressive, a loss of freedom, a denial of choice. But it can also feel liberating, Beyond the event horizon, there are no more decisions to make. The path is set. The destination is certain. All the anxiety of choice, all the burden of responsibility is lifted. You are no longer in control, and there is a kind of peace in that surrender. Many spiritual traditions speak of letting go, of releasing attachment, of surrendering to forces larger than the self. The event horizon is a scientific expression of this idea. It is a place where control is impossible, where the universe takes over completely, where the self, with all its striving and resistance, must finally yield. In this sense, the journey inside the event horizon is a meditation on mortality, on finitude, on the limits of existence. We are all falling, in a sense, toward our own personal singularities, the moments where our individual stories end. We cannot avoid these endpoints. We cannot choose not to die. The best we can do is choose how we fall, with fear or with acceptance, with resistance or with grace. The event horizon teaches us that some things are beyond our control, that the universe contains regions where our will, our intentions, our desires become irrelevant. And perhaps there is wisdom in accepting this, in recognizing that we are not separate from the cosmos, but part of it, subject to the same laws, following the same inexorable trajectories through space-time. As this journey comes to its close, as we pull back from the edge of the singularity and return, in imagination, to the safety of distant space, let us carry this lesson with us. The event horizon is real. It exists in black holes scattered throughout the universe, invisible boundaries marking regions of no return. But it is also a metaphor, a way of understanding the limits of control, the inevitability of endings, the peace that can come from surrender. You are lying comfortably now, breathing slowly, feeling the weight of your body against the surface beneath you. Your mind has traveled far, to the edge of a black hole and beyond, into regions of space-time where gravity becomes absolute and time itself transforms. But you are here, safe, in a universe of gentle forces, of structures held together by the same gravity that creates black holes, but in a far kinder form. As you drift towards sleep, let the images of this journey fade gently. The event horizon, that invisible boundary, becomes less sharp, less defined, blurring into the general darkness that surrounds it. The singularity, that point of ultimate mystery, recedes into the background, no longer a destination, but simply an idea, a reminder that the universe contains extremes beyond imagination. Feel yourself floating, not falling, suspended in a calm and patient darkness. This darkness is not the darkness of the black hole, not the absolute void inside the event horizon. It is the gentle darkness of rest, of sleep, of the mind releasing its grip on wakefulness and drifting into quieter states. The universe is vast beyond comprehension. It contains black holes, yes, regions of extreme gravity and inescapable pull, but it also contains this moment, this quiet room, this warm body, this peaceful mind. And in this moment, gravity is gentle. It holds you softly to the earth, a reassuring presence, not a threat. Time flows forward smoothly, without the strange distortions of curved space-time. Space extends in all directions, open and navigable, without event horizons or singularities. You are far from any black hole. The nearest is thousands of light years away, invisible, silent, following its own trajectory through the galaxy. It poses no danger. It is simply part of the vast ecosystem of the cosmos, one type of object among many, playing its role in the grand cycles of matter and energy. And so you can rest. You can let go of the tension, the curiosity, the need to understand everything. The mysteries of black holes will still be there tomorrow, waiting to be explored by physicists and mathematicians. slowly yielding their secrets through decades and centuries of careful work. But tonight, those mysteries can wait. Tonight is for rest, for the gentle dissolution of thought into sleep, for the simple pleasure of existing without effort or intention. The event horizon, as a concept, can even be a comfort. It reminds us that not everything needs to be solved. Not everything needs to be understood. Some things are beyond our reach, beyond our control, and that is okay. We can let them be, accepting the limits of our knowledge, the boundaries of our power, without anxiety or fear. In sleep, we cross our own small event horizon, the boundary between waking and dreaming, between conscious control and unconscious drift. We cannot observe the exact moment of crossing. We cannot hold on to awareness as we pass through. We simply let go and find ourselves on the other side, in the strange interior landscape of dreams, or deeper still, in the dreamless darkness of deep sleep. This crossing is not frightening. It is natural, familiar, something we do every night. And just as we trust this process, this daily surrender of consciousness, we can trust the larger processes of the universe, the cycles of formation and dissolution, the transformations that occur across all scales of space and time. Black holes are part of this larger pattern. They form, they exist for unimaginable spans of time, and then they evaporate, returning their substance to the cosmos. Nothing is permanent. Everything is in flux. Even the most extreme, most stable structures eventually dissolve, contributing to the ongoing evolution of the universe toward maximum entropy, toward the final state of rest. And in that ultimate rest, that heat death of the universe, far in the future beyond all imagining, there is no suffering, no struggle, no conflict. There is only stillness, perfect and complete. The universe has released its hold, let go of all structure, all complexity, all the temporary patterns that we call stars and galaxies and life. It has returned to simplicity, to uniformity, to peace. This is not a sad ending. It is simply an ending, the natural conclusion of a process that began with the Big Bang and has been unfolding ever since. And in contemplating this ending, we can find a strange comfort, a reminder that all things pass, all tensions eventually resolve, all energy eventually disperses into a calm and universal stillness. Your breath is slowing now, becoming deeper, more regular. Your muscles are relaxing, releasing the subtle tensions that accumulated during the day. Your mind is quieting, thoughts becoming less frequent, less urgent, drifting like clouds across an empty sky. The black hole, the event horizon, the singularity, these concepts are fading into the background, becoming less vivid, less immediate. They remain as knowledge, as understanding, but they no longer command your attention. Other parts of your mind are taking over, the parts that manage sleep, that guide your body through the night, that work below the level of consciousness to restore and refresh. Let yourself sink into this process. Trust it. You have done this thousands of times before. Your brain knows how to sleep. Your mind knows how to rest. You do not need to control it or guide it. You simply need to allow it, to step aside and let the natural rhythms take over. The darkness behind your closed eyelids is complete now, absolute in its own gentle way. Not the darkness of the event horizon, which traps even light, but the darkness of closed eyes in a dark room, a simple absence of visual input, peaceful and safe. And in this darkness, you can rest completely. There is nowhere you need to go, nothing you need to do. The journey into the black hole is complete. The exploration is over. Now is the time for stillness, for quiet, for the deep and restorative rest that comes when the mind finally releases its hold on the waking world. The universe continues its vast, slow evolution, stars burning, galaxies turning, black holes glowing faintly, with hawking radiation across the dark expanses of space. But you do not need to witness it. You do not need to track it or understand it. It continues without your attention, following laws that were set in motion long before you existed and will continue long after. And so you can let go. Let go of awareness. Let go of thought. Let go of the need to know, to understand, to control. Let yourself fall, not into a black hole, but into sleep, into the gentle oblivion of rest, where consciousness fades and the body does its quiet work of healing and renewal. The event horizon was never a place of fear. It was simply a boundary, a transition, a mathematical surface in space-time. And sleep is also a transition, a boundary you cross each night, passing from waking to dreaming to deep sleep and back again. It is natural. It is safe. It is necessary. So cross that boundary now. Let yourself drift across the invisible line between wake and sleep. There is no resistance. There is no struggle. There is only the smooth, continuous flow of transition, as natural as breathing, as inevitable as time. And on the other side of that boundary, there is rest. Deep, complete, restorative rest. The kind of rest that the universe itself will one day know, when the last black hole has evaporated, when the last star has cooled, when all energy has been spent and all structure has dissolved. But for now, in this moment, it is your rest, your peace, your darkness. Let it embrace you. Let it hold you. Let it carry you gently into the deep and dreamless quiet where consciousness fades and only the slow rhythm of breath remains, rising and falling, like waves on a dark and endless ocean, until even that awareness dims, and there is only sleep, only rest, only the absolute and perfect stillness of a mind at peace. Good night. Rest well. The universe will still be here when you wake.